Hello friends, today we will learn about the basic operation of single phase transformer. It is used to control the voltage level. It can be used as step up or step down transformer. To overcome the losses, electricity from the generator is passed to the step up transformer. You can see in this picture, this is the distribution system. In this case, the voltage is being step up from the grid system and is received by a step down transformer and is supplied to the homes and the industries. Transformer is nothing but a set of coils magnetically coupled. The main thing is the physical basis is the mutual induction. Two inductive coils electrically separated but magnetically coupled. Now let us see this picture. This shows a transformer. For this we need to make an arrangement of ferromagnetic material, and it has a primary and a secondary. This is type of step down transformer, from which we get electricity to our homes and industries. In this case, the primary has maximum windings and the secondary has minimum windings, so that the output voltage is decreased. The next is the step up transformer. This is generally used at the grid system. So the primary has minimum windings and the secondary has maximum windings, so we get the output voltage as large enough than the primary. Now look at this picture. This picture shows about step up and step down transformers, the voltage differences, how the voltage are different from primary to secondary winding in case of step up and step down transformer. Now next, coming to the transformer side, its operations and its basic constructions. It is made up of ferromagnetic material. It has primary and secondary winding. As you can see, V1 produces current I1 on the primary side and generates a voltage V2 on the secondary side by the principle of induction, that is the Faraday's law. First coil produces flux, circulates through the core, links to the second coil as the voltage is circulating. Flux is also circulating. There are certain assumptions like the windings should be lossless, permeability of the core is infinity, and there is no leakage. So till now you have got a brief idea about the transformer, its principles, the elements. Now we will learn pictorially. Here you see the transformer. As said before, we have attached an AC source, a switch in the primary coil and a switch in the secondary coil, and a load resistance. Whenever switch 1 is closed and switch 2 is open, there will be no linkage of flux. Even if there will be linkage of flux, these switches will be open and hence the EMF will be not produced in the secondary side. So these are some factors we need to consider regarding the transformer. Transformer is a static device in which it is magnetically coupled. So even by Faraday's law, whenever there is flux change in the primary side, that is linked with the secondary side and EMF is induced, as said before. In general, the flux produced by each coil can be separated into two components. There are two components of the flux, that is a leakage component and the magnetizing component. Each of these components is depicted by a single streamline with the positive direction determined by the application of right hand rule. So you are familiar with the right hand rule to the direction of current flow. Let me tell you what is the right hand rule. Whenever you have to curl the finger in the direction of current, then the thumb finger will give the direction of the magnetic field. The curl of our fingers will give the direction of current and the thumb will give the direction of magnetic field. If any one is known, we can find the other one. Often in transformer analysis, I2 is selected positive out of the top of the coil and placed dot. So the point which comes out of the paper or the screen, that is represented as dot, and whichever goes inside the paper or the screen is represented as a cross mark. Now regarding the flux in transformer. So in the self-inductance and mutual inductance video, we have learned about the linkage of flux due to self-inductance and the linkage of flux in case of mutual inductance. So this is the application of that part. Let phi1 is the flux in the first part, then it will have flux like FL1, FM1 and FM2. The leakage flux, that is FL1, is produced by the current flowing in the coil 1. FL1 is the leakage flux that is flowing in the coil in the coil 1, and it links only with the turns of the coil 1. Likewise, the leakage flux phi 1 2, that is phi L2, you can say, is produced by the current in the coil 2 only, and it links with the turns of the coil 2. Now let us talk about the magnetizing flux. We have magnetizing flux is M12, M1 and M2. So M1 is produced by the current flowing in coil 1, and it links with the turns of the coil 1 and 2. Similarly, magnetizing flux phi M2 is produced by the current flowing in the coil 2, and it also links with the coil in 1 and 2. So the net flux in this side, that is the phi 1 and phi 2, we can get as, in case of phi 1 there will be total number of fluxes as the leakage flux and the two types of magnetizing flux, and similar to the case of phi 2. These are some of the applications of mutual inductance concept. Now the basic principle behind a transformer. As said before, the transformer is a static device working on Faraday's law of induction. Faraday's law states that the voltage appears across the terminal of an electrical coil when the flux linkage associated with the changes. This EMF is proportional to the rate of change of flux linkages. So whenever there is a rate of change of flux linkage, we get an induced EMF, and that is what happens in case of transformer. Well, mathematically we can get the EMF equation as minus d phi by dt, and minus is given by the Lenz's law. Now this is some mechanical analogy you have to know. This is example of step down transformer. We can see three elements over here: number of turns, high voltage and low current. So as this is a step down transformer, we want to get a lesser voltage in case of the load side, so the number of turns is reduced, voltage is reduced, and current is increased. Now how it is compared with a mechanical analogy. This is the electrical part, and how it is compared to the mechanical analogy. You can see a gear train, the gear train having wheels, a larger gear and a smaller gear. Now think this is to be the step down transformer, in which the conversion takes place from the larger gear to the smaller gear, as it has taken place in case of many turns to few turns. In the larger gear there are many teeths, and in smaller gear there are few teeths. This has a higher torque but low speed, but this has a higher speed with lesser torque. So this is the mechanical analogy of step down transformer. You can also make yourself about step up transformer. Now coming to the elements of transformer. We know the source side is called the primary side, the load side is called the secondary side. In case of ideal condition, it is very important to remember the ideal condition of transformer. We generally deal with assuming that it is an ideal transformer. In case of ideal transformer, the resistance of the coils is 0, the relative permeability is infinity, 0 core and iron loss, and 0 leakage flux. So these are four conditions very important for the ideal condition working of a transformer. Again I want to say, the resistance of the coil is 0, the relative permeability is infinity, iron loss and core loss is 0, and leakage flux is also 0. Now you remember the first picture, S1, that is the switch in the primary side, and S2 is the switch in the secondary side. If switch S1 is closed and S2 is open, the core does not have a flux. The voltage induced across each coil is proportional to the number of turns. So there will be no voltage produced in that case. Now if switch 2 is now closed, that is the secondary switch is closed, a current now starts to flow in the resistance, and that is the load resistance R. This current is given as net EMF by R. Thus the magnetomotive force in case of the secondary side, that is N2I2, is applied to the magnetic circuit. This will immediately make a current I1 flowing into the dot of the primary side. We will learn it about the dot convention in case of transformer also. Just hold on. So that N1I1 opposes N2I2, and the original flux of the core remains constant. If this won't happen, then there will be a disturbance in the core flux change, and there will not be any balance between the V1 and E1, that is on the primary side. So it is very necessary to remain. And one more important thing in case of transformer is the frequency always remains constant from the input side to the output side. May it be step up transformer, may it be step down transformer. Now the induced voltage, you can see from the books there are several derivations. I'm just going with the formula. The induced voltage is given as V equals to, is very well known formula, 4.44 phi max Fn. Phi max is the flux linkage, F is the frequency of the AC source supplied, and N is the number of turns. So this formula can be applied to both the primary side as well as the secondary side. Now if you want to replace phi, we can make it as B into A, where B is the maximum permissible flux density and A is the area of the core, cross-sectional area of the core. Now this is a diagram, that is a phasor diagram of a transformer operation. You will learn about these phasor diagrams, the equivalent circuit in the higher studies. This is just to remember at this point of time, where I is the iron loss and I0 is the no load current. The magnetizing current remains perpendicular to the V1, and the resultant of magnetizing current Im and I is the IO, that is the no load current. Now let's talk about the transformation ratio. You know it very well. The transformation ratio is the relation between the voltage, the input-output voltage, current, and the number of turns. The magnetic flux in common coils is V equals to, the voltage given is given as 4.445 max Fn. Therefore, the voltage can be varied by changing the number of turns. This voltage is directly proportional to the number of turns. Hence, V1 equals to N1, V2 equals to N2, and that is equals to a constant, that is K. We know as that transformation ratio. Now there is the net power of the input and output is given as V1 I1 equals to V2 I2. Similarly, N1 by N2 equals to I2 by I1. So these are some formulas regarding the transformation ratio. These are very useful in solving numerical parts. Now, as said before, the frequency of the input and output side remains constant, but the power changes. Always remember, the power in case of transformer is given in kilovolt ampere. It is not kilowatt, as this voltage and current depends upon the magnetic circuit inside it, so the value is given as a unit of kVA. Now let's talk about the polarity dot convention. Also, our previous video of mutual inductance have given you an idea about how to apply the polarity dot convention. So let me tell you once again. Suppose in this case we have two dots in the entry side. If both of the current enter through this dot, the mutual inductance will be positive. And suppose this dot comes up here. In one case the current enters from the dot, and in another case the current exits from the dot, then in that case the mutual inductance will be negative. The terminals of different windings are of same polarity if currents entering or leaving them produce flux in the same direction of the core. Now how to check the polarity? Measure E1, 2 and E3, 4 as shown here. This is E12 EMF induced in the first coil, E34 EMF induced in the secondary coil. Connect 2 and 4. We have to connect this to 2 and 4 and measure E13, and we can measure it by a voltmeter E13. Now E13 is given as E12 and E34. If this case happens, that is E13 EMF comes up to be E12 and E34, then 1 and 4 have the same polarity. And if E13 comes up to the difference of both of them, then 1 and 4 has different polarity. It is similar to the cases of connecting the battery cells with same polarity or different polarity. Just a little bit of analysis is required in this case. Just remember, if the two voltages sum up and gives the net, they have the same polarity. If the two voltages gives the difference, then they have the different polarity. Now this is a very important task. We will study in the highest semesters, but for the time being, parallel operation of transformer is very essential. I want to mention 2-3 points regarding this. A self-owned transformer may not be so efficient to supply to a large number of people. So in that case, what happens? We need to add one more transformer to it. And how can you add that? The better method is a parallel operation of the transformer. In this case, if one transformer goes out of order, then the other will supply us, and there will be continuous supply, and we will not face any problem. Also, the rectifying process to this type of transformer is easier. So in order to give higher efficient current and continuous current to supply, we use this parallel operation of transformer. And the polarity check condition is also applicable in case of parallel operation transformer to check the polarities. Now if the polarities are wrongly connected, that is the wrong connections will give a circulating current within the windings that can destroy the transformer or can burn it. This is the correct diagram for the polarity parallel operation. The transformer must be attached to the same polarity, and if this happens in this way, there will be circulating current within the winding and it will burn it. Now transformation regulation. The loading changes the output voltage of the transformer. Transformation regulation is a measure of such deviation. We can know that the transformation regulation is given as voltage at no load minus voltage at load, full load, by voltage at full load. And if you want to calculate the percentage, just multiply it by 100. Nodal voltage means the RMS voltage across the load terminals without the load, and full load voltage is the RMS voltage across the load with a specified load. It can be full load or with some specified load. So this is the formula for the voltage regulation, and this also gives us the efficiency of the transformer. Now the most important thing, in case of transformer, we have efficiency and it is not 100%. Obviously no one is 100% efficient, so there are certain losses like iron core loss and copper loss. Also transformer suffers from two or three types of losses: iron core loss, copper loss, hysteresis loss, eddy current loss. There are many. These are the main four kinds of losses. Iron loss is given as V1 square by R, and copper loss is given as I square R plus I2 square R. That is the total loss in case of primary and the secondary side. And I have told you about the eddy current loss that can be rectified by using laminated cores also. So efficiency. What is efficiency? Efficiency is the net output by the net input. In this case, the net output is V2I2 cos phi 2 by losses. That is the net input. Input consists of the loss plus V2I2 cos phi 2. If we solve in that manner as shown, we get a very large formula but you have to be conceptually sound for this. You don't need to remember all the time. This is the output, net output, that is V2 I2 into cos phi 2 divided by net loss, that is iron loss plus copper loss plus the input. In this case cos phi 2 is the power factor, the load power factor. So this was about losses and efficiency. We have to practice more numericals on this to be conceptually sound. Now when we can have maximum transfer efficiency? The efficiency varies with respect to two independent quantities, namely the current and the power. That at any particular power factor the efficiency is maximum if copper loss equals to core loss equals to the copper loss. Whenever we have maximum efficiency, that means the core loss is equal to the copper loss. This can be obtained by differentiating the expression of the efficiency in the last slide. At any particular I2, maximum efficiency happens at unity power factor. Whenever cos phi equals to 1, that is unity power factor, we get maximum efficiency. So for maximum efficiency to happen, both of these conditions are very important to remember. That is, the core loss should be equal to the copper loss, and there will be unity power factor. These two cases are very important for maximum efficiency. You can see a picture. Efficiency rises from 0 to 1, a full load current. In case of power factor equals to 1, we have the maximum efficiency. As power factor decreases, the efficiency decreases. And at point on the x-axis, at this load current, core loss equals to the copper loss. This is a line to that core loss equals to the copper loss. Now there is an important type of transformer. I will give you just a brief idea. That is the auto transformer. Before we have read about the transformer in which the primary and secondary windings are separated from each other but magnetically coupled, but in this case the primary and secondary are on the same winding. The primary and the secondary are on the same winding, and this is named as auto transformer. It has no galvanic isolation. There are some features of auto transformer. It has lower leakage as there is no separation of primary and secondary windings, lower losses also as number of windings is less, lower magnetizing current, increasing kVA rating, and the most important is there is no galvanic isolation. Now coming to the construction of transformer, it can be of two types, that is the cell type and the core type. In case of core type, it is surrounded by the whole type, and in case of shell, it is kept in the middle part. You can see in the first picture, that is the core type, and this is the cell type. The windings are within it. Now there are various ways of laminating to reduce the eddy current loss. Here some of the pictures are shown. This is the first layer, L-shaped lamination. This is known as the L-shaped lamination, and this is known as the EI-shaped lamination. You can see here that is E and this is I. So these two type of laminations are basically used to reduce eddy current loss. So this diagram will give a brief idea about what's actually happening in case of transformer. You have been seeing transformer in the radio, in television. This is a laminated core to reduce the eddy current loss. This is the core type, in which you can find a coil 1, coil 2 surrounding this part, core. Till now we have learned about the single phase transformer, so we can also have the three phase construction also, and we can have three phase construction as three single phase connected to each other and by the bank circuit. So there are several methods to construct three phase transformer. We will know it in the higher semester studies. These are the major operation of transformer in the grid system, in the conservator.